Dear students, welcome in the CEC lectures. Here we are dealing with the characterization of nanomaterials, in which we are studying the spectroscopic studies to characterize the nanomaterials. Up to now we discussed the ultraviolet visible spectroscopy for the characterization. It is an optical method for the characterization, or we can say optical characterization of the nanomaterials done by the spectroscopic methods. So now in today's lecture we discuss about the infrared spectroscopy. As we know about the spectroscopy, that spectroscopy is a branch of science where we deal with the interaction of the radiation with the matter or with the sample which we are using. So infrared spectroscopy, where the radiation is the infrared radiations. So in this lecture we will discuss about the infrared spectroscopy. We will discuss the principle of infrared spectroscopy. We discuss about what instruments use for the infrared spectroscopy and what are the parts in this instrument. What are the applications of infrared spectroscopy where we can use the infrared spectroscopy. And last is the references. So we start with the definition of infrared spectroscopy. What is IR spectroscopy? Infrared spectroscopy is the study of interaction between the infrared radiation and the matter. As infrared radiation which is in between the visible and microwave region. These are the electromagnetic waves, and this spectrum is in between the visible and microwave region. As you are seeing on the screen, that this infrared region, the light we are using, and is in the range of 720 to 1100. So we can say this is the visible, this is the infrared region which is in between the visible and microwave region. Moreover, infrared spectroscopy or the vibrational spectroscopy, it is also called a vibrational spectroscopy, because by using the infrared radiations, molecule will vibrate. So we can say it is also a vibrational spectroscopy, which is an analytical technique that takes advantages of vibrational transitions of molecule. The molecule will vibrate in the various electronic states. So it is also called a vibrational spectroscopy. It is one of the most common and widely used spectroscopic technique which may be used for the inorganic and organic compounds for determination its structure and what type of compound we are using, that can be identified by using the infrared IR spectroscopy. And this technique of infrared spectroscopy is conducted with an instrument. That instrument is known as infrared spectrometer, or we can say it is a spectrophotometer which produces the infrared spectrum by interaction of the infrared radiation with the sample. So here on the screen we are seeing an analytical diagram, which is here we are using the IR source. The light passes from the mirrors and then it passes from the reference and passes from the sample. We are using the monochromatic light, so we use the monochromator to pass the light on the sample and the reference. After that we use a splitter, and then we have the detector. Detector will detect the light. So this is a simple mechanism where the light from the IR source fall upon a monochromator, splits the light into the two parts, one pass from the reference, another pass from the sample, and then the splitter will get the light from the reference and the sample, and it goes to the detector, and where we can find out the IR spectra. Now this is the IR spectra of ethanol. This type of output or this type of IR spectrum we can get after the IR spectroscopy, after doing the IR spectroscopy. Now what is the principle behind the IR spectroscopy? Basically this infrared spectroscopy is related to the vibrational and rotational energy level of the molecules. As we are dealing that this IR spectroscopy is a vibrational spectroscopy, and in the vibrational levels there are various rotational sublevels. So this is we can use the vibrational and rotational energy levels to get the IR spectrum. When the frequency of IR radiation is equal to the natural frequency of the vibration, then molecule can absorb the IR radiation. This is a condition for the absorption, that when the frequency of radiation which are falling on the sample must be equal to the natural frequency of the vibration of the molecule. So this is the principle of the IR spectroscopy. Apart from this, absorption of IR radiation causes an excitation of molecule from the lower to the higher vibrational level. In the absorption, molecule will jump from lower state to the higher state. Here we are using the vibrational level, so molecule will jump from the lower level to the higher level. Each vibrational level is associated with the number of closely placed rotational level. It means we are having the various rotational level in between the two vibrational levels. Means lower level and the higher level we are at the various rotational level. Therefore, the IR spectroscopy is also called a vibrational rotational spectroscopy. Here we know that in this all the bands in the molecule are not capable of absorbing the IR energy. But what type of bands are able to absorb the IR infrared radiations? Which are accompanied by a change in dipole moment will absorb in the IR region. So this is a condition for the absorption of the IR radiation, is that there must be a change in the dipole moment. Only that radiation will be absorbed by the sample. Such transitions are called the IR active transitions. And what are the inactive transitions? Where change in dipole moment of the molecule are not directly observed, and these type of transitions are known as the IR. These transitions are not allowed transition, and these are not active transition. So the system will be the IR inactive. The infrared radiation will not be absorbed. So change in dipole moment is of the molecule. The change in the dipole of a molecule is a required condition for the IR spectroscopy. What is the theory behind the FTIR? When a molecule absorbs the radiation with a frequency less than 100 centimeter inverse, here we are dealing with the wave number, not the wavelength and the frequency, but here we are dealing with the wave number, that the frequency less than 100 centimeter inverse molecular rotation takes place. If the molecule absorb more energetic radiation in the region of 10 to power 4 to 10 to power 2 centimeter inverse, molecular vibration takes place. So this is a condition for the molecular vibration. The frequency must be less than 100 centimeter. Now single vibrational energy changes is accompanied by a large number of the rotational energy changes, and thus the vibrational spectra appear as a vibrational rotational band. As there is a transition between the vibrational one level to the another level, lower level to the higher level, but this also accompanied with the large number of the rotational energy changes. What are the fate of absorption of radiation? Here there are the three main processes by which the molecule can absorb radiation. Of these routes, each involve an increase of the energy which is proportional to the light of light of energy absorbed, means as a light absorbed, increase in the energy of the molecules. So what is the first condition? First process is the first root occurs when the absorption of radiations leads to the higher rotational energy level in the rotational transition. Means when the molecule jump from the lower level to the higher level, it must be absorbed. Radiation leads to the higher rotational level, then the energy absorbed will be higher. Second occurs when the absorption of the radiation leads to a higher vibrational energy level in the vibrational transition. Transition should be at the higher level. Next, third occur when absorption of the radiations leads to the higher energy level in its electronic transitions. So these three processes are important for the absorption of the radiation, and the output will be better. So these three conditions where we use the higher rotational level, higher vibration level and higher electronic level. Here you see on the diagram, there is a energy level diagram where we are having a various electronic energy levels. The electronic energy levels contains the vibrational level. Each electronic levels have the various vibrational level, and various vibrational levels contains the rotational energy levels. So rotational levels are in between the vibrational levels, and vibrational levels in between the electronic energy levels, and all these participate in the electronic transition in the absorption. Here we are talking about the vibrational, rotation, absorption. So you see in the diagram that the energy will be absorbed and the transition takes place up to the higher rotational level, and the B part where we are having the higher vibrational level, and the C part, that is a transition in the higher electronic level. So A is the rotational transition, B is the vibrational transition, and C is the electronic transition, and all plays a important part in the IR spectroscopy. What is the criteria for a compound of absorbs of the IR radiation? First is the correct wavelength of the radiation. What type of radiation we are falling on the sample, it is very important. Second is the change in the dipole moment. As we know that only those compounds will absorb the IR radiation which obeys the change in dipole moment. So what is the correct wavelength of the radiation? A molecule to absorb IR radiation, the natural frequency of vibration of some part of a molecule must be the same as the frequency of incident radiation. It means the radiation which are falling must having the same frequency as the natural frequency vibration of the molecule. So the absorption will takes place. It means we are falling the correct radiations on the sample. Next is the change in the dipole moment. A molecule can only absorb IR radiation when its absorption occurs a change in its electric dipole. When the electric dipole moment will change, then only the absorption will takes place. A molecule is said to have an electric dipole when there is a slight positive and negative charge on its components of the atom. Then the molecule will be dipole. Then there will be electrical dipole change in the molecule. So these are the two conditions. First is the correct wavelength we should use. Second is the change in the dipole moment, which plays important role for the absorption of the IR radiation. What are the molecular vibrations? These as we are talking that this is a vibrational spectroscopy, so vibrations are very important. So we know about what is the molecular vibration. First is there are two type of vibration. First is the stretching vibration and second is the bending vibration. What is the stretching? Vibrations, where the vibration or oscillation along the line of the bond. Here we have the change in the bond length and occurs at a higher energy 4000 to 1250 centimeter inverse. These stretching vibrations are of two types. First is the symmetrical stretching and second is the asymmetrical stretching. So any absorption takes place, then these type of the stretching vibrations and bending vibrations takes place in the molecule during the absorption of the radiation. So what is the symmetric vibration? Where the two bonds increase or decrease in the length simultaneously. That is the symmetric stretching. But asymmetric stretching, where we have the increase and other will decrease. So one bond length is increased and other bond length is decreased. That is the asymmetric stretching. Then what is the bending vibration? Where the vibration or the oscillation not along the line of the bond. They are also called the deformation. The bond angle is altered, and this type of bending vibration occurs at low energy, that is 1400 to 6667 centimeter inverse. These are also two types. First in plane bending, that is the seizing, rocking, and second is the out plane bending, which is wedging and twisting. So two type of vibrations we use in the molecule. One is the symmetric vibration and second is the asymmetric, which is the stretching, and here second is the bending, which is also of two type, in plane bending and the out plane bending. These takes place when the light of particular radiations fall upon a matter or a sample. Now, why we are studying the infrared spectroscopy? As we know that we are dealing with the interaction of the molecule with the light, means light of infrared wavelength will fall upon a molecule. So we are analyzing the infrared light interaction with the molecule. Second is the portion of the infrared region most useful for analyzing the organic compound, which is having the wavelength range from 2500 to 16,000 nanometer, which is corresponding frequency range 1.9 10 power 13 to 1.2 10 power 14 hertz. So this is also important for the here we know that why we are studying the spectroscopy, IR spectroscopy. We are getting the photon energy which is associated with the part of infrared radiation, which is in the range of 1 to 15 kilocalories per mole, are not large enough to excite the electrons, but may include the vibration excitation of the covalently bonded atoms or group. Means we are using the covalent bond for excitation of the vibrations. We get the vibrational excitation. It is also known that the addition of the facile rotation of the group about the single bonds molecule experiences a wide variety of vibrational motions. So characteristics of the components can be done by using the IR spectroscopy. We can find out the various property or various characterization. Consequently, virtually all electronic compounds will absorb infrared radiations that corresponding in the energy of these vibration. Means as we know that the energy absorbed must be equal to the natural energy of the vibration, natural energy of the molecule. So we can get the vibrations. Infrared spectrometers, which is used to characterization, and this permit the chemist to obtain the absorption spectra of the compound that are unique reflection of their molecular structure. means what molecule or what compounds are present in the sample, that can be done by using the electron spectroscopy. A fundamental measurement obtained in the infrared spectroscopy is an infrared spectrum, which is a plot measure infrared intensity versus the wavelength or the frequency of the light. The spectrum which we are getting in the infrared spectroscopy is the plot between the infrared intensity and the frequency of the light. And IR spectroscopy measures the vibration of the atoms. Based on this, possible to determine the functional group. Various functional group present in the sample can be determined by the IR spectroscopy. Stronger bands and the light atoms will vibrate at a higher stretching frequency. The stretching frequency or the bending frequency we can measure by using the IR spectroscopy or the wavelength. How much stretching and the bending takes place when there is a vibrational rotational transitions between the molecules. What are the main parts of the IR spectrometer or the spectrophotometer, which is used for the characterization of the sample, or which use the IR light, means infrared radiation are used in this spectrophotometer. Then what are the main parts of this IR spectrophotometer? First is the radiation source. This is very important as we are dealing with the infrared, so the radiation source must be infrared. Second, sample cell and the sampling of the substances. What type of sample we are using? Liquid, solid or gas? For this we use the sample holder. So sample cell is very important, and the sampling of the substance. Third part is the monochromator. Monochromator which splits the light into two parts. Then detector and then the recorder. Detector will detect the light pass from the sample, and then recorder will give the IR spectra, which is the plot between the intensity and the frequency. Now, in the IR, instrument requires a source of radiant energy which emit IR radiation, which must be steady, intense enough for detection and extend over the desired wavelength. So, what are the various sources of IR radiations? Are Nernst glower, incandescent lamp, mercury arc, tungsten lamp, globus source, nichrome wire. These are the various parameters. IR spectroscopy is used for the characterization of the solid, liquid and gas samples. So solid, various techniques are used for the preparing the solid sample, such as pressed pallet techniques, means we prepare the pallet of the sample, the powder which we are using, and solid run in a solution, solid films, mull techniques, etc. These are the solid sample preparation method. Second is the liquid, where we use a sample can be held using a liquid sample cell made of the alkali halides, where aqueous solvent cannot be used as they are dissolved alkali halides. So only organic solvents like chloroform can be used in a liquid. Now, gas sampling of the gas is similar to the sampling of the liquids. So we have three types of samples to characterize by using the IR spectroscopy. Thank you. We will continue in the next lecture.